Welcome back to our good afternoon session, and so we will start hopefully just on time. So we have two very interesting presentations after this lunch break, and let's go ahead and get started with them. So the first presentation is by Mikhail Belkin from University of San Diego, California, San Diego. Michael is known for his work in theory and applications of machine learning and data analytics. And so this presentation hopefully will help us to see how theory can be applied to this notion of training infinitely large neural models.
Thank you. Thank you so much. Very nice to be here. And yeah, so I sort of changed the title a little bit. I would like to have a practical theory of deep learning, and I hopefully I'll start with discussing a little bit why we need deep learning theory and why this is an urgent necessity. And in particular, I wrote some thoughts about this actually on some sort of text about that. So I will start with that, and then I will sort of give a specific example of the theory that we might want to have, or something toward that theory of deep learning, which will be like how to basically understand feature learning in neural network. And this is joint work with my fantastic collaborators, Daniel Beaglehall, who is a student at UCSD, Ajit Radhakrishnan, who is now a postdoc at Harvard, and Parthi Pandit, who just joined IIT Bombay as faculty. Yeah, and they really drove a lot of this research. So, yeah. So let me start with I'll just start with this example, because for me, this was like particularly, I think, was kind of eye-opening, this interaction. And this was about 3 months or 4 months ago when something called code interpreter, which is now advanced data analysis, came out. And even before that, it was very impressive. But like this kind of interaction just sort of was mind-boggling to me. And why? Because you can run the code inside the system, and you can discuss the results of the code. So I uploaded some data, and you can give a command, fit a kernel support vector machines to my train data so that accuracy is perfect on train, report test accuracy. And you can see this is actually a very ambiguous command, and this is not something which is like, you know, if you ask an undergraduate student to do this, they will probably struggle with this, because how do you even get perfect accuracy on train with this type of method? In any case, this is what it does. It's like, let's try increasing C parameter to a large value. It writes this code, it runs a code, and then it reports accuracy. And this was a small part of the interaction, but that's basically what it did. So in a sense, this is like a very capable undergraduate assisted level now. And I do use it in my machine learning class now, actually, routinely. So this is pretty amazing. And, you know, what is now happening with these models? And let me just give you a very brief idea. This is a slide from Andrei Karpathy's presentation, but let me just make a couple of points. So these models are basically being deployed everywhere now. And what do we know about them? Well, there is this first stage, pre-training, which is actually should be called training, because that's the main training thing. And it's being trained on a large quantity of data, something like about 1 trillion examples, tokens, more or less. And then they try to make it more user-friendly, or more somehow improve, you know, safety, performance, usability, whatnot, by typically doing some sort of human reinforcement learning, RLHF. And that basically has something like 10 to the 4, 10 to the 5 tokens, something of that order. So now it's like the first obvious thing, and this is 10 to the 12, right? This is 10 to the 4. That's 4 orders of magnitude. I'm sorry, 8 orders of magnitude difference between these two, right? So, so how can we know that this does anything at all? So, well, it certainly improves usability, and it seems to improve, like, you know, we probably don't want it like to give us recipe for, I don't know, like a biological weapon or a bomb or whatnot. it seems to be doing something. On the other hand, like, how do we actually know that such a small amount of data can do anything? And the answer is, well, we don't. And this is from last year. It's a little outdated now, but this is kind of like the sizes of this model and the sizes of the training set. And GPT-4 is supposedly about 2 trillion parameters. They don't release the actual numbers. And it's trained on something like at least 1 trillion tokens. Okay, so this is a meme. It's known as a Shoggoth meme. Shoggoth is a Lovecraftian monster. So this is unsupervised training. It's not unsupervised. This is actually like training on the model, which is trained on the internet. And the little smiley face is like the result of this like last 10 to the 4 tokens that's used RLHF. And I mean, there is some truth to this. There is also, like, okay, well, what's the true thing about this? The true thing about it, it is truly something which is like very complex and unknown, hiding behind this kind of like friendly interface. Of course, it's not necessarily a monster. We don't have to think it's, evil or anything like that, but it is something pretty alien. And of course, you can also say that maybe the same applies to us. We're also kind of like some sort of, if you think of biology as being the hardware, we're running stuff on that biological hardware, but maybe I shouldn't go too far into that. In any case, we don't understand what this thing does, and that is clear. And I think it's fair to say that there is little hope for like safe, interpretable, aligned, whatever, choose your favorite word here, artificial intelligence without some sort of fundamental theory, because otherwise it's like, trying to cover that monster with a little smiley face. And unfortunately, there is a lot of skepticism about what theory can do. And this is a kind of example what Stuart Russell gave testimony in front of the Senate just a few months ago. And he basically said that like internal principles are largely impossible to understand, right? So there is, like leading theorists or leading machine learning experts sort of think that this is either impossible or at least impossible at this point. Of course, well, let me pose some questions about the magic of deep learning, and then I'll try to at least like point out a few things, and then point out to a few things that we can actually do. So what is the magic of deep learning? Well, first, why and when do neural networks outperform other models? We don't really understand this, but we're starting to. Second, how can Markovian models be adequate for text prediction? I won't go deep into this, but this is essentially just Markov chains, although with a very large context sizes. And sort of traditionally, it has been considered impossible for such models to, for example, generate like adequate language and so on. But it seems that they work just fine. And in particular, wise predicting training of the next token is enough. And that's not quite the same as the previous one, but it's a related issue. And what are the inductive biases for these gigantic transition matrices that we have? And just to make a point here, if you look at the context sizes of these big models, the context size is basically what the model looks for. So the way it works, the model looks at some context size, like say 1,000 tokens, 1,000 words if you wish, and then it predicts the next word. And then it shifts by one, and then it predicts the next one. It's really, really simple. It's kind of pretty amazing something like that can work. In any case, if we look at the sizes, it's about 2,000, then it's about 4,000, then 8,000, 32,000. Now, of course, it's like 100,000, right? So they just keep growing. And if you think about what it is, well, what is the combinatorial space of possibilities there? The vocabulary size is something of the orders 10 to the 4, 10 to the 5. So that's the number of words in the vocabulary. Now, if you just take context like 4,000, which is not particularly big, it's like GPT-3, not even some of them have 100,000, then the size of this whole thing is 10 to the 4 to the 4,000 times 10 to the 4. This is like a truly gigantic number. Even if your vocabulary size is only 2, this is already 2 to the 4,000, which is, you know, more than anything, any physical object you can think of. So that's the size of the matrix that we're dealing with, and somehow this model is able to fill that matrix based on just 1 trillion examples. Now, 1 trillion examples is very large by sort of any human standard, but it's not large at all compared to this numbers. It's like not even, you know, an atom compared to the size of the universe. It's much less than an atom. So that must imply that the complexity of the underlying problem is actually very low compared to what it could be just from a combinatorial kind of superficial analysis. So there is some sort of low dimensional structure there. Now, the question is, what is the structure? And let me maybe just very quickly ask you the following question. Well, what is the structure when we do any statistical inference? Like, so let's just think about, let's forget about large language models, AI, and all of that. Just think about data in 1 dimension, okay? And this is as simple as it gets. So I have, this is my X, and this is Y, right? I have these points. And we probably agree that something like that is a reasonable feat, more or less. So what makes this reasonable? Now, if you think about this problem, you can think, well, don't we have the same exact issue as with LLMs here? Why? Well, because there are actually infinitely many points here, and I need to make a prediction at every one of these points. This is like filling an infinitely large matrix. Right? So I need to make infinitely many predictions. Right? This seems difficult. So, but why do I say that something like this is reasonable? Well, the reason for this is that because of physics. And what does physics tell us? Physics tells us that if I have 2 points nearby and I have 2 sensors located nearby, then the measurement of the sensors usually are very similar, right? It's not always true, obviously. There could be exceptions, but most of the time, physical proximity means that the measurement will be similar. And that means that we expect this function to be Lipschitz, essentially. And once you say, okay, Lipschitz, there are various ways to write it in terms of various norms and so on. So there are various mathematical ways to say what it means for this function for nearby points to be similar. But basically, it's essentially just saying that the derivative is small enough. So once the derivative is small enough, you have this inductive bias. So this inductive bias purely comes from physics. Now, this is pretty interesting because once you believe in this, so you have this infinite dimensional space of all potential functions, but out of those, you are choosing the ones which have small derivative, and that's a low rank space. It has some sort of effective low dimension. So even though the space of all potentiality is infinite dimensional, the space of things which are acceptable to us because of this physical proximity bias are small. So that's basically what it is. It's physical spatial proximity, and that's what makes learning possible in this kind of classical settings. Now, this actually kind of analysis directly leads to kernel machines. I'll describe this very briefly, but that's directly mathematically, once you sort of have this, and you assume in addition that this is a Hilbert space, you get kernel machines. Okay, now we can say something a little more. We can say, well, okay, well, what about vision, right? In vision, for example, you have some sort of parallel transport, and maybe you have some sort of scaling. That's another property of the physical space, right? When I move with respect to some, object to the first order, it's parallel transport. And then you can incorporate that invariance, and then convolutions incorporate something like that. So again, this comes from physics. Convolutions come from some simplification of physics. So now the question is, well, here is a big challenge. What is the analogous thing for language? So we understand this. We understand definitely the physical, spatial proximity. But what allows us to feel those large matrices for language? That seems very unclear. Okay, so now let me Oh yeah, let me make one more point. We have to be very careful about overanalyzing existing architectures because they're full of bells and whistles, and we don't know where the bells are and where the whistles are and where the actual like engines and gears are. So it's very easy to, like have a analysis of bells and whistles without actually seeing the gears. Okay, so now let me sort of move on towards something a little more specific, and a kind of key empirical observation, and this has been, observed in maybe last 10 years, and it's nicely kind of stated here in Kaplan et al. It's basically that like greed is good, right? More is always better of everything. Number of parameters, size of the data set, amount of compute, let's just do more of everything. And that seems to really work. In particular, we can kind of tell, well, okay, well, why not just take n? N is the size of the model. Why not take n to be infinite? That's actually not an unreasonable thing because we'll see in a second that you can have infinite neural networks pretty easily. And in fact, something that worked on, we've seen that at least in some cases, just increasing the size of the neural net. So here you have the generalization error. The generalization just improves with the size of the neural net, and it seems a pretty consistent kind of phenomenon that we observe in many, many different settings. So, okay, infinite neural networks, that's actually not something really new. Marx, in fact, mentioned that in his talk too. It goes back to the theory of reproducing kernel Hilbert spaces and splines and kernel machines and so on. Very recently, it was understood that in certain regimes, neural networks are actually also this kernel machine. So infinitely large neural nets are in certain regimes exactly kernel machines. And that was first identified specifically in this paper, Jacob, Gabriel, and Hoglar. Now, let me just very briefly remind you what kernel machines are. It's a really, really simple thing. So you can formulate it as some sort of optimization of a functional norm in some infinite dimensional space. But the upshot of this is simply the following. You have a kernel, and my predictor is just going to be a sum of this kernel function at each of my data points. And now you can just think about this kernel as being a Gaussian or a Laplace function. So it's just a linear combination of Gaussians. Very, very simple. Well, actually, Laplace works slightly better in practice, so we prefer Laplace. But it's you can put a Gaussian instead of Laplace; it won't make a big difference. And moreover, this is beautiful because these alphas can be computed by simply matrix inversion. So it's a convex problem. Everything is in closed form. It's really quite wonderful. And it has this wonderful interpretation in terms of all this infinite dimensional stuff, norms and so on. Now, as I already mentioned, wide neural networks in certain regimes are equivalent to kernel machines. So there is a specific conversion which takes a very wide neural, by large I mean wide, takes a wide neural network, actually can be arbitrary depth, but imagine that the depth is fixed. You take the width to infinity, and it just becomes a kernel machine, and I can write down this kernel explicitly. There is like an explicit formula. It's quite nice again. So, okay, infinitely wide neural networks, basically kernel machines. Nice. And as I said before, infinitely wide is good because we like to have the number of parameters to be as large as possible. So that kind of like seems to be like solving the problem. And like, okay, problem solved. There is nothing left. And indeed, for some problems, this is actually state of the art. But what you realize is that something is missing. And so actually, just from a personal point of view, when NTK paper first came out, I was very excited by that. And I thought, okay, Well, this is like now we know that neural networks are just implementing kernels. Now just the question is what exactly do we do with these kernels? And then, there was like some evidence that, well, neural networks do work. Oops, I'm sorry. They do work better than kernels in some settings, and it's very hard to replicate their performance with a kernel. So why is this? And like with this complicated neural network, it's very hard to say what's going on. So there is always, maybe you need to like choose parameters a little differently. Like it's always very hard to say. But let me give you something really, really simple to show that this is not a fluke. This is actually something which happens very clearly. This is a very simple experiment. I take X in 100-dimensional space, okay? And F of X is simply X1 times X2. So it's just a function of these two coordinates, nothing else. Okay, no noise, nothing, right? Deterministic, super simple. And what do you see? You see that if you use a kernel, you train them both to have 100%, to have perfect fit on training data. And on test data, so R square, if it's essentially the square loss. Basically, 0 is bad and 1 is good. It's scaled to be 1. 1 is perfect and 0 is bad. So as you can see, kernel does very badly. And neural network basically nails the problem. This is 1,000 training points. So this is a big separation between kernel. This is just empirical. This is a huge separation between kernel and neural network. So what is going on? Like, why is it doing this? If it's just a kernel, then why is there a big gap? And surprisingly, this experiment is very recent. And as far as I can tell, the first experiment was in Wei, Li, Liu, and Ma, 2018, the first experiment of this type. I mean, this could have been done, of course, easily like 20 or 30 years ago. There is nothing special here. And there have been some recent work showing that some theoretical work basically on analyzing this. But I'll describe this in terms of like what is actually going on here. And so before I explain why this is happening, let me first introduce the following. If you have a neural network, just think about this was a fully connected neural network. So each layer is connected completely to the next layer. And suppose you have W1 as the matrix of weight for the first layer, then we call this W1 transpose W1 neural feature matrix. And it turns out that if you look at this matrix, you see something quite interesting. So what is the size of this? The size of this is actually 100 by 100. It's D by D, the size of the input. And if you just plot this, you realize that for the trained model, this only has 2 non-zero entries. The rest of the entries are close to 0, and these 2 entries are close to 1. So when you multiply your input by this is a filter. This simply filters out the first 2 coordinates. So what neural network is doing, it's learning this filter in addition to fitting the data. And here is the interesting thing. If you actually know this filter in advance, 20 data points is enough, and both kernel and neural network do equally well, perfectly. So learning this filter is key. If you don't learn the filter, you do badly. If you learn the filter, you learn really well. Okay, so now what is the nature of the filter? And the nature of the filter, if you think about it, so let me give you a different object which has the same property, and then I will kind of postulate that this is the same thing. And this different object is something called average gradient outer product. And the idea is the following. You just take a gradient. In this case, if you just take the gradient of this, you have x2, x1. And the zeros everywhere else, right? Because the derivative is 0. And you simply take that times that transpose, and you average this over your data point. Or you take expected value, whatever, if you have the distribution. And if you take expected value of this, you see it's actually a matrix with 2 ones and 0 everywhere else. And so the key is that this object, expected gradient outer product or average gradient outer product, is actually filtering out coordinates which are relevant to my predictions. And so this is not a new idea. It goes at least 20 years back, this thing. So let me tell you why this is a good idea. Now, let's think about what it does. At every data point, it looks at the direction of which direction changes my prediction. And I'm essentially just projecting only on directions which change my prediction. So directions which don't change my prediction will be 0 after you filter them out. So if you think about that previous thing that I had, 98 of my coordinates will not change my prediction. Even though my data is fully dimensional, it's a full Gaussian distribution, but the directions are irrelevant. So if I know this average gradient outer product, I can just filter them out, and I just remove those which are irrelevant. Okay, so in some sense, it measures input directions which affect response, and that's exactly what we want, right? We want to get rid of anything which doesn't affect response, because that's what we want to predict. Anything which gives us no information for prediction is probably irrelevant. Okay, so now here is a claim, and this is what we call the deep neural feature ansatz. And the claim is that these two objects are actually the same. What do I mean by the same? I have to be a little bit more precise here. I mean, first, they cannot be really the same. They're proportional to each other. Second, this is an ansatz, so this is not precise. This is just saying that when you measure those things, you get something which is highly correlated, okay? And you can make it more complicated, but I'll just talk about the first layer. And now you can measure, so you can ignore this red ones. You can just look at the green one. This is the average correlations for every layer, layer 1, layer 2, and so on, over like 120 different data sets. And you can see that the average correlation is something like 0.9. So they're very highly correlated. They're not the same. In general, they're not the same. They're the same under some special conditions, but they are almost the same. What's the upshot now? Like, what is missing now? The missing thing now, if you go back to kernels from this point of view, you realize that, yeah, we have this, but we're measuring this distance here. But how is the distance measured? And if you think about science, if you think about any predictions, you have to choose the correct features, right? Because, you know, like if you drop an object and you want to measure how long it is going to drop, right? What is the relevant feature? Well, the relevant feature, of course, is how high it is and some sort of, profile of the object with respect to air resistance. Like its color, its chemical composition, a lot of other stuff is not really relevant. Now, if you're going to predict this based on all this other stuff that you have, you're just going to predict junk, right? So you have to choose those features which are relevant for the problem. And this somehow norm doesn't, like if you just use it like that, you're giving some features. How do you know these features are any good? We don't. So the point is that this is not the right way to think about what infinitely wide neural networks do. Infinitely wide neural networks, actually, they do two things. They select a low rank matrix A, and after selecting them, they do a kernel machine. So now this is a kind of maybe correct way to think about what is feature learning for infinitely wide neural networks. It's a composition of some sort of low dimensional transformation and a kernel machine. Now, this makes it a little more difficult because for kernel machine, I have this nice convex problem. With this thing, it's not convex anymore because I have to learn two things at once. But, the last 10 years told us that we shouldn't, or 50, whatever, some number of years. Like one lesson we learned is that non-convexity is okay. We shouldn't be afraid of it. And well, this actually directly leads to this new algorithm we call a recursive feature machine. So what you do, you take your data, you build a predictor to fit your training data. And then from this predictor, you compute this estimate of this matrix, of this low rank matrix. And then you recompute the distance using this matrix. So you rescale the data. And then you repeat. So it's a kind of iterative process. You first do predictor. Hopefully this predictor is not completely random. There is a little bit of signal, because if it's completely random, of course, it's garbage in, garbage out, but maybe there is like a little bit of signal there. With that signal, you estimate this matrix, and then you plug this matrix back in and you improve the predictor. So this is this iterative process. And the beautiful thing about this is that this is actually an average. So even though like computing, this is an extremely noisy estimate of the gradient of the true function, but because you are averaging it over like the whole data set, presumably you are going to be okay as long as your bias is not too much. So that's basically the algorithm. Now you can use it with a Laplacian kernel, and it's actually a very nice algorithm. You basically just take this kernel, fit it by inverting the matrix, explicitly compute that matrix M, and then just recompute. So everything is closed form. There is no backpropagation, nothing like this. It's a linear regression, essentially. Rescale, linear regression, rescale, and so on. You know, repeat. In practice, it's like 5 times. Okay, now let me give you back that example. So what you see is that you do this, and once you do this trick, you essentially learn the same filter as the original neural network, and the performance is the same as a neural network. So we can replicate. This method is, on this data set, is equivalent in performance to neural net. So now let me make a couple of points about neural networks versus RFMs, recursive feature machines. Neural networks optimizes fit to data and projection operator by minimizing the same loss function using SGD. This is very interesting because neural network does 2 things with the same loss. First thing, it wants to fit the data, right? It wants to drive the loss to 0. Second thing, it wants to select these features. Now you have these 2 processes which are controlled by the same parameter. So it's very tricky to trade off these parameters because you know that's why neural networks are kind of fiddly, because like depending on how you choose initialization, how you choose step size, what is the size of the neural network, all these parameters, they control both of the things. So and you want both of them happen. So if it's too fast, right, gradient becomes 0 before features can be selected. If it's too slow, then you just never converge. So it has to be somehow, you have to find this Goldilocks type of regime. Second, it's a weird thing that evaluation loss is not equal to the training loss. It's like we think of training loss as a proxy for the evaluation loss. This story is completely off because they say, oh, well, we cannot optimize classification loss because it's not differentiable. So we take a proxy loss, which is something like cross entropy. No, this is off. If you just optimize directly the classification loss, you won't get feature learning. Doesn't work. It does 2 things. Now, here is the interesting thing for RFM. The loss is identically 0 at every step. There is no, it's not related at all to your loss function. It's a completely different process. So feature learning is completely decoupled from loss minimization. Okay, so now, yeah, you can actually see this works really well. And like, so basically, I'm pretty happy to claim that whenever fully connected neural network works well, we can get better or equal performance using the RFM. Let me skip this, but yeah, we can. Here is a really interesting example, and so let me maybe discuss this one because I think it's quite interesting. So this is training a neural network. This is a number of epochs, and the data set is very simple. It's just 2 classes from CIFAR10, so these are images. But I'm cheating here because there is like a star here, and this star encodes a class. So there are trucks and there are planes. If this is a yellow star, this is a truck. If it's a black star, it's a plane, okay? So in principle, it's very, very easy problem. But if you just do it, you don't know which features it should pay attention to. So if you run an ordinary neural network, you see an interesting phenomenon. After about 90 or 100 iterations, you get 100% training accuracy, but your test accuracy is still pretty bad. It's only 80%. And as you continue training, despite the fact that the training accuracy is 100%, right? So classification loss is perfect. There is nothing to. But of course, the loss that you use is still not zero because it's a continuous thing. So it still continues to do feature learning. And you can see that by 150 epochs, it gets to about 96 or 97%. And you can see that after about 80 epochs, you can see this little star here. The feature matrix already identifies a star. After 150 epochs, it's much cleaner. It's very similar to something they call grokking, which I don't want to discuss right now. In any case, you can do the same thing with RFM. And RFM, you see after first fit, it's junk, right? Your accuracy is only 55%. But even from this extremely junky prediction, you already get very good identification of the features. After 2 iterations, you get like 90 plus, and the features are even more clear. In 3 iterations, nails it, it's 100%. So that's kind of what is happening here. Now, we ran this on like 120 data sets from UCI, and this is actually state of the art on tabular data. It beats every other method by like fairly significant amount, about 2% or so. So, and it's much faster than the neural net as well. Oops. I don't have time to talk about this, but this actually it's quite interesting because it's closely related to sparsity. And there is something called iteratively reweighted least squares. And essentially a linear version of RFM is essentially iteratively reweighted least squares, and it actually works really well, like instead of lasso. You can use RFM. And if you do this for matrix completion, you get low rank. You get actually it's superior to nuclear norm of minimization. It's but it does something similar to that, which was actually observed with neural networks. But now we have this much cleaner way of doing low rank matrix completion. But yeah, like something like this. This is like a sparse model with 1,000 coordinates, just 12 data points, kind of is already enough to identify. Lasso would do something similar. Okay, I'll skip this. Let me show some pretty pictures. You can do the same thing for convolutional neural networks. And for convolutional neural networks, okay, I don't want to like describe the ansatz, but it's something similar, but you have to do the AGOP with respect to patches. And the ansatz is actually very strong for convolutional neural networks. Now, these are like all kind of state-of-the-art or close to state-of-the-art kind of ResNets and VGGs and so on architectures. And you get, as you can see, you get like at least 0.8 or 0.9 kind of correlation. So it's ansatz is actually holds very well for these architectures. And in fact, the interesting thing is that you can extract features directly from like some of these neural networks like VGGs. So this is an AGOP of the image at a certain layer, and you can see that it actually like highlights certain features. And in fact, you can, well, hopefully we can, it's sort of like saliency map, but it's a different process. And you can say, for example, with a dog, it kind of highlights the eyes and so on. So you can, hopefully this is more interpretable. I'll give another example, which is also clear that it's interpretable. There are these data sets, so you can play the same game with a kernel for convolutional neural networks, and at the very least we can beat plain convolutional neural networks with this method, with this kernel. The problem is to get state of the art, you have to take these very complicated kernels, which are just very expensive to compute. So it's like we need like 1,000 GPU hours to do these computations. But at the very least, like a plain vanilla, we can beat like a plain convolutional neural network on this task, on which non-convolutional things just don't work at all. And even convolutional kernels don't work that well on this without feature learning. Okay, I'll skip this. Oh yeah, this is another cool thing. If you look at the eigenvectors of this feature matrix, you actually recover it's essentially some sort of wavelet. It's a wavelet basis, which was noticed for AlexNet before, but we can directly get it from this gradient outer product. Actually need very few samples to get this. Okay, I'll skip this since I'm almost out of time. Let me give you some examples for transformers because everybody loves them. Same thing holds for transformers, and this is so this is quite interesting. So what you do, you take eigen. Oh yeah, I should. Sorry, I forgot to mention one thing. The eigenvectors of this M matrix are basically the filters, right? So if you want to think about the filtering of that M matrix, these are just eigenvectors of this AGOP. And if you do this for transformers, this is a GPT-2 transformer trained on this tiny stories data set, which is kind of nice, relatively small data set that's much more tractable. And if you look at the top some of the top eigenvectors of this, you see that it actually corresponds to words. So these words, these tokens, have high projections onto these eigenvectors. And you see these words actually have very nice semantic interpretations, right? You have like food, you have adjectives, you have some like common words like, you know, also, still, then, and so on. Like preposition stuff like that. You have verbs and so on. And you can even like go over the text and you can highlight the words. Like these are highlighted corresponding to a certain eigenvector, which corresponds to names and animals. So I think that's kind of what we want. This is a little too primitive right now. It's not at the point when we can really interpret something like GPT-4 because it's only like, so these eigenvectors have semantic meaning, but not enough yet. But it's just show that this is, you know, presumably we should be able to do that. Okay, so let me now, I'm out of time, so let me conclude. Maybe I spend 2 minutes to conclude. I think what we have seen is that there have been immense resources concentrated on a narrow class of models. Extremely impressive results, sort of beyond all expectations, but there is no reason to think that these are optimal. In fact, there are all reasons to think that these are probably not optimal. Unless we get some fundamental understanding of this model, we will not understand the output because clearly the structures are inside the model. And I think this ansatz produces, like, gives us one specific way that we can hope to understand it, by connecting essentially the properties of the weight matrices to properties of the model itself with respect to the inputs, this gradient outer product. I think we need a kind of physics-style theory. It's not necessarily that we prove everything. It's nice to prove things, but it's really unnecessary. In physics, people don't, you know, like the law of gravity is not proved. Nothing is really proved, but yet it's a very precise mathematical statement. We have to be careful about overanalyzing existing architectures, and I think the fact that we can replace fully connected neural network with this other architecture, with RFM, suggests that alternatives exist, and they can be quite different. They're not backpropagation based necessarily. And I think there is a lot of evidence that such theory is possible. So, okay. I mean, that some of this evidence is recursive feature machines. And I think we will definitely can push this to get results for things like transformers and so on. And I'll just finish with this picture, well, two pictures. This is a current deep learning, right? And if you have seen the movie, it's Howl's Moving Castle, which is a beautiful movie. It's this is a magical moving castle operating by magic, right? Just like deep learning. It does amazing things, but it's kind of hard to know which part of it is essential. Actually, it has a fire demon inside. So hard to know what's involved. What we would like to do, we would like to convert it into something like this, right? This is a bullet train. It's also a very complex machine, but it's actually operated, and you need a lot of people to understand its functioning. But like we actually understand aspects of its functioning. They're based on some sort of solid understanding of electricity, mechanics, and kinematics, and so on. So I'll stop here. Thank you.
So very nice talk. I didn't quite understand the experiment you conducted where you said that your model is similar to transformers. What did you do there? What was the training?
It's not similar. It is transformer.
Yeah.
It is GPT-2.
Okay. So, but
it's a transformer.
Okay.
You extract that matrix, expected, average graded outer product, because you have the model. You can just differentiate it, and you extract this matrix. You look at the eigenvalues.
Okay.
Eigenvectors of this matrix, and you look which tokens have big projections onto this,
Okay.
and that identifies semantic categories.
I see. Okay, got it. Okay, thanks.